Okay, so colligative properties. Colligative properties are properties of solutions that get affected by particles, and not the identity of what those are. It's just the fact that there's particles there, okay? Colligative means that it's a collection, and these things include vapor pressure lowering, which we're going to talk about what vapor pressure is again, because we talked about that, but I don't know necessarily if you remember that from the IMF section. Boiling point elevation. So what do you think that means? Boiling point elevation. Huh? What does elevation mean? Height. So it's increasing the boiling point.
Oh, I got it right.
Freezing point depression. So what do you think that is?
The opposite.
Right, it's going to lower, but this time it's freezing point. Okay? And then something called osmotic pressure. I'm not going
to.
Yeah, it has to do with water pressure, okay? And the pressure that's caused by that. All right, so let's go back and kind of review vapor pressure again, okay? Because we need to kind of remember what that is. So remember vapor pressure. If you have a sealed container and you have a liquid in there, if you have something all the time, you've got some of the water molecules going into gas molecules and some of the gas molecules going into water molecules. Remember that?
Yes.
It's kind of this transfer back and forth. It's sealed, so nothing's leaving the container. Okay? The gas molecules then are going to exert pressure on the sides of that container. So that's what vapor pressure is. Does that make sense? Okay. So then, if you talk about vapor pressure lowering, these colligative things, these solute particles, are going to prevent some of that from going up into the gas phase, thereby lowering the pressure exerted on the container by those gas molecules. Does that make sense? Okay. All right. So let's talk about why that happens. Ionic compounds are electrolytes. They're going to disassociate in water. They form a solution that's going to conduct electricity. Why does it conduct electricity? And they are ions. What is an ion again?
Doesn't it just have a charge?
Yes, it has a charge, and that charge then is able to conduct electricity, okay? As opposed to putting a covalent compound in there, like sugar, okay? It doesn't have a charge. It's not going to conduct electricity, okay? So these electrolytes, many are going to produce ions that are strong electrolytes. Some of them are going to be weak. So some of them come apart a lot, like sodium chloride, and other ones don't come apart very much at all. And that's when you had like your slightly soluble, if you remember back to this chart, you had SS on here, slightly soluble. So one of those examples on here is aluminum fluoride, okay? So aluminum fluoride would be a weak electrolyte because it's not going to come apart very much, so therefore it's not going to conduct much electricity. Molecular compounds, so things that are covalently bonded, do not ionize. They don't conduct electricity. They're not electrolytes. There are some exceptions, but very few. Okay? So let's talk about freezing point definition or depression and how we know that this happens. Okay? At a solvent's freezing point temperature, the particles don't have sufficient kinetic energy to overcome interparticle attractive forces. What do we use instead of interparticle attractive forces? IMFs, okay? So these IMFs come together, they link these compounds together, and you freeze. It's a solid then, okay? What happens then, like if we have a sample of water, if we put salt in that, okay? So now we're going to go through and we're going to put some salt in here. Okay, if we put salt in there, that's going to interfere with those IMFs. So it's going to prevent those IMFs from forming at that temperature. It's going to have to freeze at a lower temperature in order for the IMFs to take hold. This is why they put salt on the roads during the winter. Okay, so they put salt on the roads, and that's going to interfere with that ice forming. But if we're in a really cold spell, like, you know, below zero, they don't bother to put salt on the road. They just put sand. Why?
Traction.
Right. Sand will give you traction. Okay. The salt is ineffective at that lower temperature. It's not going to cause enough interference that it's going to prevent the ice from forming. So that's why they don't put salt on the road all the time. Sometimes they'll put sand out. So it just depends on what the weather forecast is. If it's going to be too cold, the salt, they're just going to waste money by putting it out there. Okay. So that is freezing point depression. We can actually calculate how much that depression will change things. Okay. So this is the equation that we do that. And this sign here, delta, that means change in. So this is how much your temperature is going to change from that normal point. So water, for example, freezes at 0 degrees Celsius. We run through this calculation and it tells us what we're going to subtract from, in this case, 0. Okay. So there's different components of this. The I is, it's a Van't Hoff constant, but I call it the interference factor. Okay. I think that's easier to remember, but if you were to look it up, that's what it stands for. Okay. So this is an interference factor. This only, so how many, what this comes down to is how many things is this going to break up into? Okay. So if this was in water, which we're going to put it in water, how many pieces would a single ion or single compound unit break apart into? 2. You're going to end up with Na and you're going to end up with Cl minus. So your interference factor here is 2. The Kf value then is for your solute, and that has to be given to you. Okay, so you just have to find that in a chart. So for water, that's 1.86. And then we have to multiply that by little m. Do you remember what little m stood for?
Molality.
Right, molality. So we've got, oh, I forgot this guy up here. We'll have to go back up and do him. So this is molality. So we've got to figure out molality for this. So remember, molality was moles of solute over kilograms of solvent.
Cool.
Okay. So we have to figure out what moles of this are. So we've got to divide this by its molar mass. Molar mass for NaCl, 1 sodium and 1 chlorine is 58.5. So we're going to go 100 divided by 58.5, and that's 1.71.
I think it was short.
Huh?
This unit was short.
Yeah,
How many more units do we have?
2.
Two.
Huh? 1.71.
Oh, right. My bad.
Now, the next one is grams of water. Sometimes they will, instead of giving you grams, they'll give you milliliters. But for water, the density is the density of water. It's easy. 1. It's 1 gram per milliliter. So for every gram, you've got a milliliter. So for every milliliter, you got a gram. So if you see milliliters of water, it's the grams of water as well. Does that make sense? All right. So we need to get this into kilograms. Remember that in 1 kilogram, you have 1,000 grams. So all we have to do is move the decimal point over. So that's going to be 0.500. So we're going to calculate our molality here. Divided by 0.5. So that is 3.42. So 3.42. Now we're going to multiply these things together. Times 1.86 times 2. I get 12.7. Okay. So this right here, water, we take 0 minus 12.7. That's going to give us negative 12.7 degrees Celsius. Now let's go up here real quick to fancy old Google and go Fahrenheit or Celsius to Fahrenheit. I could calculate it, but it's just easier to do this. So negative 12.7, so that's 9 degrees Fahrenheit. Okay, so if we are below 9 degrees Fahrenheit, okay, that salt on the roads is going to be ineffective. So they're like, we're not going to waste our money putting the salt out. That makes sense?
I got it.
Okay.
We gotta go back up.
Yeah, I know. I forgot this guy. I'm sorry, guys. Bad Lippy. Bad. I enjoy some of this math stuff. And especially when it's like a practical application kind of thing like this with like the salt water and stuff. It's kind of, I don't know. It's kind of neat. It's like where you can actually see chemistry like working out in your life. I nerd out on it. Sorry, guys. All right. So we've got the same equation. This is a molecule, though. So how many things is this going to break up into? Nope, this is not ionic. 1. It's just going to stay by itself. So the I factor here is 1. This is still water, so it's still going to be the 1.86. And then we've got to figure out our molality. So here we have 100 grams of this. So 100 divided by the molar mass of,
No way.
yep.
Right.
So 100 divided by 180 is 0.556. So that's 0.556 for the moles of this guy. Okay, 180 is the molar mass. So I took 6 times 12, 12 times 1, and 6 times 16, and I added those together. That's how I got 180. I happen to have that one memorized. All right, let's pretend that this said, let's pretend that this said milliliters here. Okay, it's still going to be 500 grams. Make sense? Okay, because you got a couple on your homework tonight, so I want to make sure that you know how to do those.
Sounds good.
All right, so this is going to be 0.5 kilograms. All right, so 0.556 divided by 0.5. This is 1.11. Okay. So here, water normally freezes at 0. Now it's going to be depressed or reduced by 1.11 degrees. So we're going to end up with negative 1.11 degrees Celsius.
Why don't you have to, like,
You have to put in your equation.
Oh, crap. You guys are right. You're so smart. Lippy's so dumb sometimes. I get ahead of myself. Where's my brain? All right, let's try that again.
Oh, appreciate your graduation.
Okay, so I got to multiply that by 1.86, and that ends up being 2.07. So that ends up being 2.07, and then I'm going to take that from 0. So 0 minus 2.07, negative 2.07, and that is my answer. And that would be degrees Celsius. That's going to be the new freezing point for water.
Okay, so the last one we can just keep it in Celsius.
Yeah, I wanted to talk to you about this one because this is something that you see. And you think, I believe most of you guys think in Fahrenheit. You know, that's what we're kind of used to. So that's why I wanted to take this one and go into Fahrenheit, just to talk about, like, you know, why they do things like they do for the roads and stuff like that. Does that make sense?
What's your favorite city in Australia?
All right, let's keep going. Vapor pressure lowering, then we talked about that, how those solutes are just going to get and interfere with the surface area. So you're going to get fewer of them going up into the gas state, and that's going to reduce the vapor pressure. So we kind of talked about that one. And then boiling point elevation is just the opposite. Okay. So here we're going to take a solution where we have calcium chloride in it, and we are going to boil this. And they've already given us the molality, which is really kind of nice. So we're going to figure out how much this is going to be elevated. Okay. So what is my interference factor here? 3, because I'm going to end up with a Ca2 plus, and then I'm going to end up with 2 Cl minuses for a total of 3. So that's where I'm getting my I from. My Kb, I'm going to find water up here. That is 0.512. And then I'm going to find my molality, which they already gave us the molality, which was really nice. So we didn't have to calculate that. So 3 times 0.512 times 1.5, that's going to be 2.3 degrees change. And this time, this is elevation. So instead of subtracting, we are going to add. 102.3 degrees Celsius.
Okay, Joe, as well. So the continent of what you think is Australia, it also includes New Zealand, Kiribati, Micronesia.
All right, last thing in this unit, Ben, is osmosis is the diffusion of a solvent through a semi-permeable membrane, and it's actually not just a solvent, it's water. Okay, that osmotic pressure then is the amount of additional pressure caused by the water molecules that move into a concentrated solution. So if your solution is more concentrated, you're going to get more pressure because it's going to increase the amount of water that's going to come across that membrane. Okay? And that, folks, is chapter 14.
Cool. Okay. Time to work.
Okay? So